The next step that we take after infinite sequences will be called infinite series. So from a sequence, we're going to be able to generate a new sequence by just adding the terms together, adding the successive terms. So if we have a sequence, A1, A2, all the way up, we can start making what we call partial sums. And so we have the first term of our partial sums is just the first term of the sequence. The second term of the partial sums is the first two terms of the sequence added together. And so we see that each new partial sum is created by adding the next term in the sequence. And so on all the way to S sub n, we have the first n terms being added together, A1 through AN. This gets really cumbersome to try to write. And so we use series notation to write this concept together. And so we have A sub k is going to be our summand, what's being affected by our series. And we have this k, which is going to be called our index. You see it's written here as well. This little bottom section tells us where our index should start. So we're starting at a value of 1. The top tells us where our value should end. Our index value should end at n. And so we would have this is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 all the way up to a sub n. And so that's our series notation. What we're going to be doing often is writing the infinite series, or simply the series. And so that's going to be when we have an infinite set of numbers, such as our infinite sequence, and it's going to be written as a sub 1 plus a sub 2 plus a sub 3 plus an ellipses. We might write ellipses, then a sub n, and then more ellipses. And again, these are both kind of cumbersome to write, so we can also write it in series notation, where instead of writing that we stop at some n, we just write an infinity up there to say that this never stops. So if we have some sort of number L such that if we take the partial sums as a sequence and we look at the limit as that goes to infinity, that's going to be equal to L, then we say that the series is convergent. Important thing to note here, this is the limit of the partial sums, not the limit of the terms. So we call these our terms here. This is not this. So these are not the same. So it is important that we note that when we say that a series is convergent, we're talking about the partial sums converging. And we'll talk more about what that implies for a sub k later. We'll also say then that the series, if it converges to L, has the sum L. And so we can write down that the series is equal to L, like that. If our partial sums diverge, we'll say that the summation here diverges and has no sum. So if you add a finite number of terms, you can call that S sub n. That is the nth partial sum. The sequence of partial sums is, as it says here, extremely important. And so that sequence of partial sums is going to help us, if we look at the limit, find the value of the infinite series. So if those partial sums, as it says here, tend to a finite limit, the infinite series converges. If the partial sums have no finite limit, then the infinite series diverges. So we're going to be presented with series that look like this, and this by itself does not tell us really anything about does the series converge or diverge. We have to figure out what the partial sums are, because this is the sequence that tells us whether this guy converges or diverges. So looking at an example here, we have an infinite series, and as it says in part A, we want to find the first 4 terms of the sequence of partial sums. So if we do that, we have to look at where our index starts. We're going to look at S sub 1, and we're going to limit the top number. S sub 1 means we're going to have this index up here. We still have to start at the same place. And so when we do that, all we are really doing is plugging in 1 here. So we have 1 over 2 times, 1 times 2. And when we do that, we just get 1 over 2. If we're looking for S sub 2, the second partial sum there, then we're looking at starting from 1 and going up to 2. And so when we do that, we take the previous partial sum here and we can add on the next term. Or we can start from k equals 1 and move up in that way. Either way, we're going to be then plugging in 2. So plug in 1 here, plug in 2 here. So we get 1/2 plus 1/6. That's 3/6 plus 1/6, which is 4/6, which is 2/3. All right, so that's the second partial sum. Now we look at the third partial sum. So again, we change the upper limit here of our summation to 3, and we have the same summand here. And so again, we're going to be either taking our partial sums, taking our index, plugging it in, increasing it by 1, plugging it in, and then increasing it by 1 once more and plugging it in. So we'd put in 3 here. Or we could just take this 2/3 here and add the last term. So 2/3 plus 1/3 times 4. So that's going to be 2/3 plus 1/12, which gives us 8/12 plus 1/12, which is 9/12, which will give us 3/4. Right, and then the fourth partial sum here, k equals 1 to 4 now. And so when we do that, we'll go ahead and just write 3/4 plus 1 over, we plug in 4 here, 4 times 5. So 3/4 plus 1/20. And so we get 15/20 plus 1/20, which gives us 16/20. And so our end result there is 4/5. So our sequence of partial sums looks this way. We've got 1/2, 2/3, 3/4, 4/5, and so on. And from this, we can, as it says here, find an expression for S sub n and make a conjecture about the value of the series. Conjecture about the value of the series means, does it diverge or does it converge? If it converges, to what? Right. So we can see here that there is definitely a pattern happening between the numerators and the denominators here. First term has a numerator of 1, second 2, third 3. So it looks like the numerators are just going to be n. The denominators look like, well, the first term is 2, second term is 3. It looks like it's just n plus 1. And this is going to be for all of our natural numbers n. So this means for all n as an element of the natural numbers. So we have then our partial sums given as a general term here. So if we take the limit as n tends to infinity of our partial sums, that's the limit as n tends to infinity of n over n plus 1, and we can go ahead and evaluate this guy. We'll first divide both the numerator and the denominator by the largest power of n seen in the denominator. So we've got 1 over n and 1 over n. So we get the limit as n tends to infinity of 1 over 1 plus 1 over n. As n tends to infinity, this guy goes to 0, and our solution here is 1. So we can say that the series from k equals 1 to infinity of 1 over k times k plus 1 equals 1, because our partial sums, in fact, have a limit value of 1. So we were able to say then that this guy converges and what it converges to. And so we look for the ability to write this pattern of partial sums down. Again, this guy here does not by itself tell us directly whether we are going to converge or diverge. We have to figure out, if we're looking at a summation, we have to figure out the partial sums. That's the sequence that's important for us. So again, we'll write the first 4. We've got -1 to the first times 1. That's -1. For 2, we've got -1 plus, and we plug in 2 for this. -1 squared times 2. That's -1 plus 2, which is just going to be 1. S sub 3, we've got 1, add on the third term, so -1 to the third times 3. That's 1 minus 3, which is -2. S sub 4, we've got -2 in the previous, and then we add in where k is 4, negative 1 to the 4th times 4, negative 2 plus 4, and so we get positive 2. And so we can kind of see the pattern here. It looks like we're both alternating signs and the magnitude is growing. And so we'll state that so far, the partial sums are oscillating and also growing. So we say growing in magnitude. And so we imagine what happens as we keep going out on these partial sums. We can say it is reasonable to say the limit as n tends to infinity of s sub n does not exist. So k equals 1 to infinity, our series here diverges. All right, so that's a couple of cases where we can figure out what the partial sums look like via just sort of writing them down a piece at a time, and then evaluating the limit, or at least taking a look at it here. So we'll kind of step on to more generalized versions of this, or maybe we can't look at just the partial sums. We'll look at a specific case. But basically the roadmap from here on out is going to be some version of given a series, does it converge or diverge? And so that's going to be essentially the rest of the unit. So we'll start looking at some different examples now. So we've got infinite series, sequence of partial sums, right? We've established that. And so now we'll take a look at another kind of factoid here. To evaluate an infinite series, we're wanting to determine a formula for the sequence of partial sums and then find its limit. And so we'll look at a specific series, geometric series, and then another nice kind of example, the telescoping series. These are going to be very formulaic. The problems aren't going to be too varied. And that's going to be nice for us in a way because it means that we'll actually be able to figure out what these series will limit to, what they'll actually be equal to. So first off, we look at a geometric series. A geometric series is going to be related to a geometric sequence. All right, so we saw a geometric sequence last time where we had each term is the term before it multiplied by some r, some common ratio. So in this case, we're just adding all of those terms together. So we're looking at the series from k is 0 to infinity, and then we've got a times r to the k. And we've got a and r fixed numbers, where a is our first term, and then r is going to be that common ratio. All right, r can be positive or negative. Neither of them should be 0. If either of them is 0, then this is just the infinite series where the terms are 0, and that's pretty boring. So we've got this theorem here. It's going to be very closely related to the convergence theorem that we had for the sequence. So now if we have a series, if the absolute value of r is less than 1, then our series converges. And in fact, the sum is given by, this is an important formula you're going to have to memorize. If the absolute value of r is greater than or equal to 1, then the series diverges. Right? The idea is if r is equal to 1, then we're just adding a to itself over and over and over again an infinite number of times, which has to diverge. And if it's greater than that, we're actually multiplying by bigger and bigger numbers. All right, so that's going to be our driving theorem for this next little section here. So we're going to be using that. So evaluate the following geometric series or state that it diverges. So we can tell that this is a geometric series because we can see that this numerator is staying the same, but the denominator is getting bigger by that 100 every time. So what we'll want to do is figure out, first off, what is a? It should just be the first term, 9 over 100. Next, we'll figure out the common ratio. And one way of doing that is just, kind of imagine what do you multiply by this to get to this. A similar way of doing that is to divide. Right? We take one term and divide it by the term that came before it. Right? So we'll have 9 over 100 squared times, if we're dividing by a fraction, we flip the fraction to multiply. And so we get 1 over 100. And so from there, we can form our geometric series. So we're looking at from k equals 0. It is important that you do start with k equals 0 whenever you're using this method. You could start with k equals 1 if you do make a modification here, but we're wanting to follow this formula to be consistent. So we're going to say the first term is a, and that necessitates k being 0. So we'll do k equals 0 to infinity, and we've got 9 over 100 times 1 over 100 to the k. So that's going to be our geometric series. And we'll go ahead and analyze r now. So absolute value of r is the absolute value of 1 over 100. So when we take the absolute value, we've got 1 over 100, which is less than 1. And so this guy will have to then converge. Right, so we see up here r less than 1. Sorry, absolute value of r less than 1. So the series does converge. Right, and so we have to figure out then what does it converge to? It's going to be a over 1 minus r. So 9 over 100 over 1 minus r, which is 1 over 100. And so we get 9 over 100 divided by 99 over 100. So we get 9 over 100 times 100 over 99. The hundreds cancel. 9 goes into 99 11 times, into itself once, and so we get 1 over 11. And so this also shows us a way that we can kind of write down a fraction as an infinite series, which will come up later as well. We're going to have throughout this chapter, throughout actually the next couple of units here, we're going to have sort of property theorems, and there's going to be a lot of kind of essential pieces that we'll need to make any real complicated series. So if we have a series that converges to A and a real number C, then we have this kind of, we probably have seen this before with derivatives, with continuity, right? This is a constant multiple type theorem, right? If we have each of our terms is multiplied by a constant, we can actually take the constant out and evaluate. Right. Similarly, we have our additive property here. If we have one series that converges, another series that converges, and we just add each term, or subtract even, then we can actually separate the summation and evaluate separately. The last one is very much dependent on specifically this series idea. Whether a series converges does not depend on terms added or removed from the series. If a finite number is added or removed, then convergence or divergence does not matter. So what is basically happening is, it says here, if m is a positive integer, then if we change the index from 1 to any other positive integer, then it's not going to change the convergence or divergence. Either both converge or both diverge. The value is going to change, though. The value of the convergence series does change. So the idea is, whether a series converges or not is essentially going to depend on, if we kind of graph a function, right, we can see that if we look at the limit as x tends to infinity on this function, let's just call it f of x like usual. Essentially what we're saying is, if you take a look at this limit, it doesn't matter if you sort of start your limit calculation here, or if you start it here, or if you start it here. Any way you look at it, this guy is going to go to 0 in this case. So that's more or less the idea that we're looking for. The end is what really matters here, the tail of the series, we call it. All right, again, evaluate or state that it diverges. We take a look at this and see that this is, in fact, going to be a geometric series. We see A here is 1, so we have 1 times r to the k. R is the important piece. Absolute value of r is the absolute value of 1.1, which is going to be equal to 1.1, which is greater than 1. So the geometric series from k equals 0 to infinity of 1.1 to the k diverges. And this is going to be essentially the way that we're going to need to write our answers for most problems in this chapter. We're going to need to end with a statement that says the whatever series it is, or later on whatever test we use, state what the series is itself, what the actual representation is, and what it does. So either converges or diverges. All right, evaluate again or state that it diverges. Geometric series will always be able to evaluate if it converges. So we'll take a look at this guy and see that it does not look like that proper form. That proper form being k equals 0 to infinity and then ar to the k. So what we're going to have to do is modify this so that it does look like the proper form. So what we'll need to do is manipulate the summand here. So we've got 2 times 1 over negative 3 to the k. If we just sort of separate out everything that has a k on it and everything that doesn't, this is usually the best tactic for a geometric series to get it in a proper form. All right, then we can actually change this fraction to 1 over negative 3 to the k, which is negative 1/3 to the k. Which now the summand looks to be in the proper form, but we have an issue where k is actually equal to 1 here. So that means that a is not going to be equal to 2 here because we have this mismatch with our index. So what we're going to have to do is we're going to actually have to plug in our first k value to get what the first term is equal to. It's negative 2/3. R, however, is still going to be whatever has the k on it. So you have negative 1/3. So the absolute value of R is the absolute value of negative 1/3, which is 1/3, which is less than 1. So this guy should converge. And so if we want, we can rewrite this in the proper form with k equals 0 to infinity, negative 2/3, negative 1/3 to the k, if we wish. However, it's not necessary. We've kind of gotten all that we need already. So we're looking for a over 1 minus r. In this case, that's going to be negative 2/3 over 1 minus r, which is negative 1/3. That gives us negative 2/3 over 1 plus 1/3. That's negative 2/3 over 4/3, which will get negative 2 over 4, which is negative 1/2. So that's going to be what we converge to, right? So we go ahead and write down our statement stating that the geometric series and we rewrite the series, k equals 1 to infinity of 2 over negative 3 to the k, converges to negative 1/2. All right, so that's going to be our answer statement there. And you can throw in a therefore at the beginning there if you want to. All right, so now that we've kind of seen the modifications that we can kind of have to our summand, we'll go ahead and take a look at this one. Again, if you have mixtures of sort of things to the k and things that are not to the k, you want to separate them. So here we see that we have a couple of exponents that include both k's and constants. So what we want to do is rewrite so that we have the k powers on one bit and the constants on the other. Remember that if you have addition in the exponent, that's the same as multiplying the two bases. And if you have subtraction, it's actually going to be the same as dividing the bases, but we'll go ahead and say that it's multiplication by a negative. That works too. All right, we'll go ahead and solve our, or rather evaluate our exponents here. We've got negative 1 to the k, 2 to the k times 2 times 3 to the third over 3 to the k. And so we'll kind of, again, take all the stuff that's to a k power, put it together. k equals 1. And again, this is something that we're going to have to write down every line, just like our limits. Make sure that you write this summand down every time. So we've got 2 times 3 to the third is 27. Then we have negative 1 times 2 over 3, all to the k power. So we get k equals 1 to infinity, 54 times negative 2/3 to the k. And from here, we can go ahead and, again, figure out what a and r are. Really, you should be figuring out what r is first so that you know if you actually have to figure out what k is, or sorry, what a is. Because if this r is going to cause us to diverge, there's no real reason to figure out what a is. R is negative 2/3. Absolute value of r is the absolute value of negative 2/3, which is 2/3, which is less than 1. So this guy is going to converge, which means we do have to figure out what a is as well. And so we go ahead and just plug in. Since we don't have 0 here, we do have to plug in 54 times negative 2/3 to the first. So 54 divided by 3, and then times 2. So 54 divided by 3 is 18, times 2 is 36, so we get negative 36. So we can go ahead and figure out then a over 1 minus r. So that's negative 36 over 1 plus 2/3. That's negative 36 over 5/3. And so when we go ahead and flip and multiply, we got negative 36 times 3 over 5. So that's negative 108 over 5. And therefore, the geometric series, and we can go ahead and just call it geoseries. And we've got k equals 1 to infinity, negative 1 to the k, 2 to the k plus 1 over 3 to the k minus 3, converges to negative 108 over 5. So that's our answer. Right, so that's what happens when we kind of have extra numbers interspersed as multiples inside of our summand. As you can see in this next one, we actually have a difference going on. And like we said before, we can actually take sums or differences inside our summand and split them up into 2 different series. And so that's the tactic that we'll want to take whenever we have 2 geometric series either added or subtracted together inside a single summand. So we'll have 2 different series to work with. So we have k equals 1 to infinity. We have 5 times 1/2 to the k for the first series, minus k equals 1 to infinity of 1/3 to the k. And so now we'll have 2 separate series. We'll go ahead and take this one and call them r1 and a1. So let's see, r1 is 1/2. Absolute value of r1 is the absolute value of 1/2, which is 1/2, which is less than 1. So this guy is going to converge, so we do have to figure out what a is. A sub 1 is going to be, well, it's going to be just plugging in k equals 1 there. So 5 times 1/2 to the first, so 5/2. Next, we look at r sub 2 and a sub 2. So r sub 2 is 1/3. Absolute value of r sub 2 is the absolute value of 1/3, which is 1/3, which is less than 1. And again, you probably do want to figure out both r's first. If one of these guys diverges, the whole thing diverges. In this case, both of them will converge because r is less than 1, that absolute value, rather. So then we figure out the first term of our second series. Plug in k equals 1, we get 1/3 to the first, which is 1/3. And so as a result, we can do the same formula on both of these guys. We've got a sub 1 here is 5/2 over 1 minus r sub 1. That's our first series, minus, we've got our second series here, 1/3 over 1 minus 1/3. So we've got 5/2 over, we've got 1/2 here, minus 1/3 over 2/3. So we get 5 minus 1/2. So we get 10/2 minus 1/2, and so we get 9/2 as our answer there. Therefore, the geometric series we write this up, k equals 1 to infinity of 5 over 2 to the k minus 1 over 3 to the k converges to 9/2. Right, so let's see. Oh, I missed one there. So looking at this last one, again, we kind of see the extra little constant in our exponent, so we're going to have to split that off. We also see here that we're starting out with k equals 2, which will modify our first term even further. So we got 1/3 to the k, and then 1/3 to the negative first. That's going to be 3. So we're looking at 30 times 1/3 to the k. So now our summand is in the form we like. So r is 1/3. Absolute value of r is the absolute value of 1/3, which is 1/3, and that's less than 1. So this guy is going to converge, so we do have to figure out what a is. We go ahead and plug in 2 here. That's our starting index. So 1/3 squared. That's 30 times 1 over 9. And so we get 10/3 as our first term. And so we'll go ahead and write that into our formula. A over 1 minus r. So we get 10/3 over 2/3. So we get 10 over 2, which is 5. So the geometric series, we copy that down again. K equals 2 to infinity of 10 times 1/3 to the k minus 1 converges to 5. All right, so that's really a good representation of the different sort of mishmashes of different problems we can have with geometric series by either sort of combining in these multiples or by even subtracting or adding different series together. So we'll kind of look at this last one and then see what we got here. Again, we want to take this and convert it into our standard kind of form for our geometric series. And to do that, all we really need to do is flip the fraction, and now it's to the k power. So we can examine our r. R is negative 4/3. So absolute value of r is the absolute value of negative 4/3, which is 4/3, which is greater than 1. Therefore, we know that this series must diverge. So the geometric series and what we can do as an alternative to sort of writing down the entire series each time is we might just say and we can say it's r value. So we can do this whenever we have a divergent sequence because that is the contributing factor here. The reason that it diverges is because of r. With the geometric series that converge, we do have to write down the original series because we are going to state what it converges to, and that's very specific to the series itself. All right. So that's kind of the difference between the two answers that we can get. If we diverge, we don't have to write the whole series every time. We can just write what the r was that made that happen. With a converging series, we have to write down the series because we're also going to write what it converges to. All right. For kind of an application of these geometric series, we could talk about infinite decimals. If we have an infinite repeating decimal, we're actually going to be able to use geometric series to write a repeating decimal as a fraction. And the idea is we're going to want to write this down as a sum of an infinite number of terms. The way that we're going to do that is by adding up these different repetitions. So we've got 1.035 bar is going to be equal to 1 plus, and what we're going to want to do is write down each repetition. So we got 0.035 plus 0.00035 plus 0.0000035, and so on. Right? So each repetition is going to be its own term. From there, we want to write it as a geometric series, which means that we want to write each term as being multiplied by some common ratio. Right? It looks like we have this 35 here, or maybe 0.035. We can say that our repeating part is our common ratio if we want. This is to the first power here. Sorry about that. Multiplied by something to the, well, we do want to write this as a r to the k, and we would prefer to put k equals 0. Right, we see that 0.035 repeated each time, and each time it's just been multiplied by something. Right, so we see that 0.035 here, we see the 3.5, we see the 3.5. Each time it's just been multiplied by something. We would want to start with the 0 power here. We want to express the next term as 0.035 times whatever it is to the first power, plus 0.035 times whatever it is to the second power, and so on. So we want to be able to figure out what is now the common ratio. So one way we can kind of work that is, again, by taking the later term and dividing by a previous term. And in this case, we can just move the decimal over. So 1, 2, 3 times here, and 3 times here. And then let's just move it twice more. There we go. So we'll go ahead and get our divisor moved all the way over. Get our dividend moved all the way over. That way we have no decimals in our fraction. And we got a common multiple here. We got 1 over 100 when we cross out those 35s, essentially. So we've got 1 over 100. That's actually going to be our common ratio. Right? We're going to write down as a decimal as well, just for consistency's sake. And so that's going to be our common ratio. And so we can rewrite this then as a series starting from k equals 0 going to infinity. We have 0.035 times 0.01 to the k. And so that gives us our a value, which is we wanted to start at k equals 0 so that this guy could be a. And our r value is going to be 0.01. If we take a look at the absolute value, we do see that we have 0.01 that's less than 1. This guy should converge. I mean, obviously, it's going to be equal to whatever this guy is. So we can go ahead and write down using our formula 0.035 over 1 minus r, which is 0.01. And so when we do that, we get 1 plus 0.035 over 0.99. And so we can also rewrite that. We can move the decimal point over 3 times. We got 35 over 990. Then we can start working through simplifying this fraction. 5 goes into both of these. It goes into 35 7 times. And it goes into 990. Let's see, it goes into 9 once. It goes into 49. Let's see, 9 times. And then it goes into, that's 8 more. There you go. So we get 1 plus 7 over 198. Real quick check to see if 7 goes in here. We got 58. Nope, it doesn't. So this is going to be our simplified fraction. One little note is that if you have a problem like this on a test, your 4-function calculator is not going to be able to reduce this fraction for you. You will need to do it by hand. Right? If you try to do this with a calculator, you'll just get back this repeating decimal. So the last thing we want to do is add the whole number on to our fraction. And so we'll get 205 over 198. And so we were able to then write down this infinite repeating decimal as a fraction. And you can do that with any repeating decimal in the same way. All right, so that's a pretty cool kind of application of this. We'll go ahead then and after this now, this is going to kind of wrap up our little talk on geometric series for now. We'll move into another type of series called a telescoping series. So with geometric series, there is a formula for the sequence of partial sums. That's that A, right? That A over 1 minus R guy. Not many infinite series can be subjected to this sort of analysis. In fact, this is the only one that we're going to work with that we can really do a formula with. With another class of series called telescoping series, it can be done. It's going to be different for each problem, though. So we can, this is the only other type of series where we'll actually be able to figure out what the sum is of our series. But it's not going to be just one formula for, one size fits all. So what we'll want to do is, as it says here, we want to express our terms as, and by terms we mean the terms in here, our summand. We want to be able to talk about them as a b sub n minus b sub n plus 1, sort of its own little sequence. If we can do that, there will be a lot of collapsing that happens between one term and the next, and the whole thing will sort of telescope. So there's a bunch of internal cancellation that's going to happen in our partial sums. So we'll go ahead and take a look at this guy here. This is certainly going to be a geometric series, but when we are dealing with it as a subtraction here, we see that we have b sub n here and a b sub n plus 1. We see that we have what looks like a term of a sequence and the term of the sequence that comes after, and it's the previous minus the next. When that happens, we can, in fact, deal with this as if it were a telescoping series. So we'll go ahead and write out S sub n. And so we'll just write out the first few terms of this series. So we'll plug in 1. That was a bad 3, I'm sorry. Minus 1 over 3 squared. Plus, we plug in 2. 1 over 3 squared, minus 1 over 3 to the third. We plug in 3. 1 over 3 to the third, minus 1 over 3 to the fourth. We can plug in 4 if we want. But we can kind of see what the pattern is going to be. And so all the way down the line, we'll usually want to write down the last couple terms here. So let's do n minus 1. If we plug in n minus 1, we got 1 over 3 to the n minus 1, minus 1 over, if we plug in n minus 1 here, we get n. And then finally, we plug in n itself, 1 over 3 to the n, minus 1 over 3 to the n plus 1. And as you can see here, there's not really too much of a reason to have these parentheses stick around, so we can essentially pretend that they're not there. When we do that, we can cancel a lot of stuff. We've got 1 over 3 squared, 1 over 3 squared, to the third, to the third, to the fourth, to the fourth, to the fifth, with the next one will be to the fifth, the sixth, the seventh, all the way up to the n minus 1th, and then finally the nth. As you can see here, this 1 over 3 to the n minus 1 does not have anything that can cancel with it. So we end up with 1 over 3 to the first, minus 1 over 3 to the n plus 1. That's going to be our partial sum. So we get 1/3 minus 1 over 3 to the n plus 1. So that is S sub n. Since we have S sub n, we can figure out what this series should be equal to by taking the limit of those partial sums as n goes to infinity. So we'll take the limit as n tends to infinity of 1/3 minus 1 over 3 to the n plus 1. As n goes to infinity, this guy gets to a huge number in the denominator, so this guy goes to 0, the fraction itself. And so we just get 1/3. And so the telescoping series then will converge to 1/3 because we were able to find S sub n. For the telescoping series, and we'll write down what the series was that we were working with. 1 over 3 to the k minus 1 over 3 to the k plus 1 converges to 1/3. All right, so as I mentioned, there's only two different series that we're going to work with throughout this entire chapter that we'll actually be able to figure out what does it converge to. Oftentimes we'll just know, does it converge, does it diverge? Sure, it converges, we don't know what to. So the only things that we can actually figure out the sum are geometric and telescoping. But wait, you may ask, we did an example earlier in this very section that didn't look like a telescoping series and didn't look like a geometric series. In fact, it was this problem right here. So for this one, we just sort of plugged in 1, then plugged in 2, and just added them together until we got a pattern. But this is actually a telescoping series. It's just sort of hidden. It's not really in the form of a telescoping series because we have a fraction that needs to be broken up. The way that we break up fractions, remember, is partial fraction decomposition. So we got 1 over k times k plus 1. These are both simple linear factors. And so we can write each of them with just a constant over top. We clear our denominators by multiplying by this guy here. We get a times k plus 1 plus b times k. Right. If k equals -1, then 1 equals 0 minus b, so b equals -1. If k equals 0, then 1 equals a times 1 plus 0, so a equals 1. So our partial fraction decomposition looks like this. We've got our fraction will look like, sorry about that, we've got k minus 1 over k plus 1. We plug in a, we plug in b. So we can rewrite this series as the sum from k equals 1 to infinity, and we've got 1 over k minus 1 over k plus 1. And so we can look and see that it looks like two terms of the same series being subtracted, and we've got the later term being subtracted by the former, from the former term. That is telescoping series. And so we can write out S sub n. We plug in k equals 1. Add, plug in k equals 2. Add, plug in k equals 3. And I'll usually stop there and then go up to the n's. So I plug in k equals n minus 1. Add, and then plug in k equals 1. Sorry, n. And then we can see what cancels. We got the -1/2, the 1/2, -1/3, 1/3, -1/4, 1/4, -1/5, 1/5, and so on, all the way up to the last cancellation we see is -1 over n and 1 over n. And so our final partial sum here will be 1 minus 1 over n plus 1. And so again, we can figure out what our limit of partial sums is as n tends to infinity by just taking the limit of our formula that we've just gotten to. And when we do that, we can go ahead and see that 1 over n plus 1 will tend to 0, and so we get the solution 1 here. So that's going to be the sum of our series, the telescoping series. And we write 1k equals 1 to infinity, 1 over k times k plus 1 converges to 1, which matches up with what we saw earlier in the section. So this is actually a telescoping series, just kind of hidden. And so when you have a fraction that's got partial fraction decomposition possible, chances are we're going to have to do it. And so now that we've seen that these telescoping series can kind of be hidden, we'll take a look at another one. In this case, we have a natural log, and it doesn't really look like anything that's going to be very nice to just kind of look at. So we think about what else can we do with logarithms? Well, we have a logarithm law that says if we have the argument expressed as a quotient, we can actually split it up into the log of the numerator minus the log of the denominator. So we're looking at natural log of, and I should probably use brackets for that one, natural log of the numerator minus the natural log of the denominator. So this looks a little strange. It's almost the wrong order, right? We would like to usually have the later term minus the previous term. And so we'll go back up and observe our telescoping series. And then think about what happens if we have b sub n plus 1 minus b sub n. How do we get that? Well, if we take b sub n minus b sub n plus 1, that should be equal to a sub n, and we apply a negative to both sides, there we go. We got what we want. So this is still a telescoping series. It's just that all of your terms will end up negative, which is totally okay, because as we've seen by that constant multiple rule, we can actually take the negative out and apply it as we want. So we'll go ahead and figure out S sub n. Plug in n plus 1 first. Natural log of, well, I guess I don't need the brackets this time. Natural log of, we plug in 1, we get 2 minus natural log of 1 plus, plug in k equals 2. Natural log of 3 minus natural log of 2 plus, we plug in 3, we get natural log of 4 minus natural log of 3, and so on, all the way up to we plug in n minus 1. Natural log of n minus natural log of n minus 1 plus, we plug in n itself. Natural log of n plus 1 minus natural log of n. And so we get a little bit of a difference here. So the cancellation is kind of in a different order. We have natural log of 2 minus natural log of 2. Natural log of 3 minus natural log of 3. So we'll kind of go to the first term of the previous, the next term of the second. First term of the previous, next term of the second, and so on. All the way up to we have, well, we can actually see what's the last one and kind of work backwards. The last one that cancels is natural log of n, and so the previous one should cancel as well. You can always write more terms just to convince yourself that this is true, and I encourage that. I know that sometimes this can be a little difficult to visualize. Just write enough terms that you can trust yourself there. So the only terms we have left, natural log of n plus 1 minus natural log of 1. Natural log of 1 is 0, so we are just left with natural log of n plus 1. So we go ahead and take the limit as n tends to infinity of our partial sums. This should be equal to our series here. And when we do that, we end up with limit as n tends to infinity of the natural log of n plus 1. This guy goes to infinity, which means that our partial sums do not converge, right? Infinity is not a number. So since our partial sums do not converge, they diverge, our series must diverge as well. So the telescoping series from k equals 1 to infinity of the natural log of k plus 1 over k diverges. And so we see that there are definitely some ways that we can kind of hide when we have a telescoping series. You're going to need to keep your eyes open for when you might have partial fractions going on. Also when you might have maybe some log laws or something similar that you might have to apply to get that telescoping series. And that wraps up then the two types of series that we can actually determine the sum for. The only two types of series that we can actually determine the sum for will be telescoping and geometric. So when we come back next time, for our next section, we'll start looking at tests for determining if some other series will converge or diverge. And we'll no longer be able to tell what it converges to if it does converge. So I'll see y'all next time.